Hi guys. So in this video, we're going to look at the D latch, understand the circuit diagrams for it. We'll look at the function table. Then in upcoming videos, we'll handle the D flip-flops. And after that, we'll learn how to draw the timing diagrams for both of them. Okay? So let's get to the big idea behind the D latch. Why do we need the D latch in the first place? So if you recall, when we handled earlier in this series, when we started sequential circuits, we were able to cover the gated SR latch. So that's what I'm trying to draw now. So we kind of see why the D latch is absolutely necessary. So remember, we introduced our enable signal with 2 AND gates so that we're able to decide when our circuit reacts to inputs. Okay, so this is our output of this, a second NOR gate. All right, then we have our output feedback together between gate 1 and gate 2. Okay, so remember, this is our enable signal. We'll call that E. Let's say this is reset, this is set. After Q follows reset, and not Q follows set. Okay, so if you remember the function table for the SR latch, it's pretty memorable. Okay, it's simple to handle. SR and output Q for now. If we had both of these as 0, then remember we said that there's no change in our circuit. If only set was high, then output Q becomes 1. If only reset was high, then output Q becomes 0. But remember, if we had both of these high, then this is an invalid state. It's a forbidden state. Okay, so even in the implementation video I did in this series, we're able to see that when we made both S and R high, then that means it is possible that Q and not Q could be the same thing, which isn't allowed in Boolean logic, which is why we didn't. Is an invalid state. We just don't go there in the first place. So this is the main problem we have when dealing with gated SR latches. It's really cool that we've been able to come up with a way that our output Q follows our inputs S and R over here. But we still have a problem where making both of these high is going to make Q invalid. And this little obstruction is what makes us kind of think of creative ways to combat this. Okay, how can I design my circuits that even though I've created an enable signal, which is I've created a situation where I'm able to decide when my circuit reacts. How do I now prevent the invalid state from happening when both S and R are 1? So how do we do this? A way you can think about addressing this in the first place is to tie them together. Okay, so let's say you have, because these are designed with users in mind. So if I give my user, instead of giving my user the liberty of 2 inputs for both S and R, right, let me just give him 1. So this technically is still going to be R, this is going to be S, but there's only going to be 1 input since we're tying them together. Okay, so what's going to happen in this situation? If S is 0, and S leads to R, so this is 0 and this becomes 0. Okay, then we see that we have no change in our circuits. But if this S, recall this is the only input we're dealing with now with our little modification. But if this S becomes 1, then R will become 1 too. And then we'll be back to where we started with the invalid state, which is absolutely exactly what we've been trying to avoid. But we're on the right track, right? Because the way to combat this issue is to reduce the number of inputs. And the actual way this is done is to invert your inputs before it gets to R. Okay, so let me do an inverter before it gets to R. So now stay with me. Okay, let's understand how this became the game changer. If S is 0, okay, because this is the only inputs we're dealing with. Because in the SR latch, usually you have 2 inputs, S and R, going into, like you know what I mean, right? We had 2 inputs going this way, but now these 2 inputs are able to be toggled by the user. But in this situation, in our makeup circuits now, we have only 1 input that's tied to R. But the only difference now is that we're inverting S before it gets to R. So while this is S, this is going to be R. So let's watch what happens. If my user inputs 0, okay, so if S is 0, then 0 still comes into this input. Then R is being inverted, okay. So while this would be 0, what comes out of the inverter is going to be 1. So this is going to be 1. And so let's say I enable this high, then we're going to have a, okay, so that's high. We're going to have a 1, and we're going to have a 0, which is the case for sets being 0 and resets being high, case 3. All right, so let's look at the other scenario. What happens when my set is high and my reset is low? Okay, so if I make my set high, that's 1. So 1 comes over here. So 1 gets to the inverter, 0 comes out of the inverter. So I have 0, and we're assuming my enable is high. So that's 1, 1. So 1 comes into sets and 0 goes into resets. And that's case 2. Okay, which is where Q becomes 1. So I hope you're able to see what happens now. Where before, with the gated SR latch, we're able to have the unstable situation of both S and R being 1. Now, by tying them together this way, okay, by linking S to R and tying them together, we're able to make sure that it is not possible for S and R to be the same thing. So that's the idea with the D latch, okay. We're able to come up with a solution, a way to combat the invalid states. And now we're able to avoid that entirely and stick with the 2 allowed combinations, which is S and R being 0 and 1 or 1 and 0. So let's draw the D latch actually in this situation to see how that applies to real scenarios. Okay, so we'll start with the AND gate. Okay, so this is the gated D latch. Well, D latches are always going to be gated. They won't have much use if they weren't gated. Okay, because it won't be able to store or latch onto the value. Okay, so let's see. So this ties second AND gate. Okay, coming to our second NOR gate outputs, feedback, okay, and then we have our inverter before we tie them together. So now when usually we would have had S and R, this becomes one single input D. Okay, so now you don't have 2 inputs S and R. You have only one input, which is D. Okay, so this is still going to remain your enable. This is going to be not Q, and this is going to be Q. So let's follow this through. Let's draw the function table for this. Let's see what happens when we tie these guys together. Okay, so the purpose of our enable input is to make sure that it's to decide when our circuit reacts. Okay, otherwise it doesn't change. So let's go enable data and output Q. Okay, so when enable is 0 and our data is 0, okay, let's follow this too. So data being 0, so that's D here, 0. Okay, so pardon, that's 0 here, 0 here, 0 here. Then recall 0 gets inverted to 1. Okay, so 1 and 0 is 0. 0 and 0 is 0. So if you remember 0, 0 going into our SR Latch configuration is going to mean that no change happens at all. So you now come to see that whenever my enable is 0, so even if my enable is 0 and my D is 1, I'm going to have no change. No change in Q at all. Because enable is what actually sets up my circuit in motion, okay? Because if the output of this AND gate is not 1, then there's nothing that's going to be able to, then this is always going to be 0 and there's going to be nothing that changes in the circuit. So let's now get to the more interesting scenarios of the D latch. Okay, turning enable on and seeing what happens. So if my enable is high, okay, so my enable being high, so that means this is a 1 and this is a 1. Then I want to write my data. So D being 0 in the first place. So let's see what happens. Data being 0. So 0 gets here and it gets inverted as a 1. So that's 1 over here. So remember from the SR latch, okay, that this was sort of resets, okay, and this was technically sets, okay. So it's just because we tied our inputs together that it got reduced to D, but the same logic still follows. This will still be the set line. This will still be the set line. So the output of 1 and 1 is going to be 1. The output of 1 and 0 is going to be 0, okay. And if you recall from the SR latch truth table, resets being high and sets being low means my output Q is going to be low, okay. I'm going to write it low. We covered that in the last video where we actually walked through each combination for the SR latch. But once my set is 0 and my reset is high, I'm going to clear my output. So remember we said enable high and data being 0, then my output Q clears, turns to 0. Cool. The last combination of this, okay, so enable stays high. The last combination of this is when my data signal is high, okay. So that's enable high and data high. So we're making data high. So this AND gate is going to be 1 and 1. So that's 1 outputted here. 1 comes here, gets inverted to 0. So 0 and 1 is going to be 0. So 0 goes into the reset line, okay, and 1 goes into the set line. So when you remember that set being 1 and reset being 0 means our output Q is going to be 1, okay. So Q is 1. So this is everything you need to know about the D latch. So now if you look closely, you can see now that as long as my enable is high, then my output Q is always going to follow my data D. So that's what this happens. Usually the D in the D latch can stand for two things, okay? But usually you see it's standing for or meaning data, okay? Because it's a data latch, it's used to store data, or you can see it's being referred to as though this is less common, the delay latch. All right, so the basic idea is what we've been able to show now. We made a sequential circuit where my output Q is always following my input D, provided my enable signal is high. All right, so this is a very important concept when you come to microelectronics and computer architecture. At a basic elementary level, is a way of storing data, okay? If you want to keep data in registers, if you have a memory segment that you want to write to, okay, because if you've got a piece of, I don't even signify this, okay, so if you've got a piece of memory to be allocated, right, you usually want it to copy what you want to write to it. So if I'm bringing a string of bits, right, and I want to copy this into a certain register, I would very much like for the output on Q to be the same as the data coming in. So computer architecture, memory storage is one very important application of the D latch. So that's what we've been able to cover in this video. But then we run into another problem when we realize that we're still dealing with the D latch, and that is because we're dealing with the D latch, we're being level triggered. Okay. So anywhere you have an enable signal, you know you're being level triggered, which is wonderful for small scale applications, but fails on large scale as you increase in size and complexity because it's not timed. All right, so in the next video, we'll look at the D flip-flops, understanding how we're able to combat level triggering by applying a clock input on the two AND gates. And from there, we'll look at the timing diagrams for two of them and how to determine when the output Q is high, how it reacts to being level triggered and being clock triggered, especially when dealing with the D flip-flop.